And yeah, I've been doing CAT stuff for a long time, and I'll talk about that. But I'll just tell you about it. So basically, like at my stage of career, I feel I could tell you stories, and through stories, you'll learn the field. Instead of it being a talk where it's a lot of math and experiments and all that, I want to kind of relate to you through stories where the field has gone. And I think through stories, you'll get an appreciation of what's going on. But towards the end, and actually, I'm going to shamelessly insert things as I go to try to make myself look really important in the field. So occasionally I'll inject things that say what I did. And that's because, I have a chance to try to tell you I did good things. And then towards the end, I'll talk about the experiments, actually this paper. So I'll talk about the work I'm doing at the University of New South Wales. I'm currently on sabbatical. So I'm working at the University of Calgary, but I'm at the University of New South Wales on sabbatical for a few months with Andrea Morello's group. And then towards the end, I'll tell you we had a theory paper, robust macroscopic Schrödinger's cat on a nucleus, and a Nature Physics paper out this year, published in January, Schrödinger cat states of a nuclear spin QDIT silicon. So I'll get to that, but that'll be a short part. So I'll kind of give you a high level view. And then this is a cat, and we know scientifically, if a picture of a cat makes you feel good, so you guys are relaxed and feeling nice in the picture. Okay. So just to go back through the history, so the history of cats goes back to Schrödinger. And I got two pictures from his papers, and I used the short DOI. So DOI, Digital Object Identifier, DOI.org has a hash function. So if you go to DOI.org and you type in basically 10/ and then 6 alphanumeric code hash, then the paper will pop up. So it's a very short, efficient way of telling you where the paper is. This is representing Schrödinger's paper on the cat paradox. And this is Schrödinger's paper on solving the Schrödinger equation for the case that the potential is a harmonic oscillator. And it's interesting, both of them are important to start the talk. And so the cat state, so the original cat state paper is different from the way we talk about cat states today. So if you go through Schrödinger's paper, you'll see that there's essentially a radioactive particle, there's a detection. If there's a radioactive decay, then the radioactive particle will be detected and cause the release of a poison gas that kills the cat. So in a very simple picture, it's really a story of entanglement between did the nucleus decay and the cat's alive? If the nucleus decays, the cat's dead. Nowadays, when we talk about cat states, we talk about essentially a macroscopic state and a superposition. So nowadays, we'll say that the cat is in a superposition of dead or alive, whereas Schrödinger's paper was more about the entanglement between the radioactive decay and the cat. And so if you think of Geiger counters, ways to detect radioactive decay, you kind of think it's a probabilistic event. But in nuclear physics, you describe an alpha particle decay. An alpha particle is a helium nucleus bouncing inside the nucleus. It doesn't just escape. It's in a superposition of being inside and outside. So if nuclear physics, the liquid drop model is correct, then the radioactive decay is a superposition. And then that leads to this whole paradox. How can a cat be in some state of being alive and dead? But as I tell people here sometimes, I'm not the language police. So originally it's the entanglement. Now it's the cat superposition of alive and dead. Whatever people say, whether it's historically accurate, I just go along with what we say. Okay, then the other thing about Schrödinger's work, so from 1926, I think, he solved the Schrödinger equation and then his own equation, and then he has the wave packet. It's a Gaussian wave packet, and he shows that this Gaussian wave packet is a solution to Schrödinger, where the Gaussian wave packet is moving back and forth harmonically, which means that the period of the oscillation is independent of the amplitude, how far it is out, and the state is the minimum uncertainty state, and the minimum uncertainty doesn't change over time. And later with Glauber, so Glauber basically, tell you a little bit there. I've actually talked to Madeline Glauber about this issue. So back in 1960, the laser was invented, not just one, but 6 different lasers. And the theorists would all think about Fock states, number states. And so there became this puzzle about what came out of a laser. So it was like 1960, 6 different lasers were invented, but it was not till about 1963 that the theory settled down with a proper explanation. in the 1950s, and if you go to the book by Heitler in 1958, you'll see that it was all saying, well, light is made of photons. How do we explain light out of a laser in terms of photons? And then Mandel and Glauber had a disagreement. That's what I remember talking about them, where Mandel would describe things in terms of photons. And the argument was that if you send a laser beam through a beam splitter, you'll get a little bit of anti-correlation between the beams. And Glauber said no, that if you split the beam, then it'll essentially be independent. And then Glauber told me that he sent papers. He tried to get him into optics journals, but they wouldn't accept it because there was a lot of politics going on. So eventually he had to send a physical review letters. And then this is the paper that got him a Nobel Prize in physics. And you can see here that the coherent state, which is a superposition of Fock number states, is kind of the antithesis of what a number state is. So in quantum mechanics, the essence is complementarity, wave and particle. The number states represent particle-like behavior, and the coherent states represent wave-like behavior. And that coherent state is this one. Schrödinger didn't call it a coherent state. It was in Glauber's Nobel Prize-winning paper, we shall call the alpha K coherent states. Their use is well known in discussions of the harmonic oscillator and the classical limit. And of course, the point there is Glauber's thinking about, the electromagnetic field has modes. There's nothing nonlinear going on. The electromagnetic field is just a collection of modes. Every mode is a harmonic oscillator. So he's just said, maybe if I think of the right mode, I can understand things in terms of that oscillator. And then in this paper, he talks about, detection theory, dipole detectors, and kind of shows how natural it is to make use of these coherent states. In my way of thinking, it's really what was clever in the debate at the time, primarily Mandel and Glauber, but others were involved, of what comes when you send a laser field through a beam splitter, and whether it's independent or anti-correlated, is really getting clear the picture of wave particle. So if you're going to do things where you have a laser beam and it's wave-like, then use a wave-like description. It's more natural. That's my take on it. So if we're going to talk about superposing coherent states, we need to get the idea. I'm going to go later into different kinds of coherent states. So just remember what we call a coherent state, ideally in this case, is a minimum uncertainty state with an unchanging uncertainty over time. And the expectation value, the mean of the wave packet, follows the classical evolution ad infinitum. Later, I'll generalize the idea and we'll sacrifice. We have to, as we go to different kinds of cat states, we'll have to make some sacrifices. Now, we can go to mathematically, the Schrödinger cat state. And when did the first paper come out on that? This was in 1974, Dodonov, Malkin, and Manco. And actually, Dodonov is in Brazil. He had his 75th birthday during COVID. So I was online, but I had a chance to discuss. So I kind of got the history right in my mind. This is a beautiful paper if you're a mathematical physicist, and an awful paper if you're not, because you have to know a lot to read it. Historically, it's the first, but it was ignored, mostly ignored. But they're essentially asking about the properties of, like the Glauber displacement operator, unitary displacement operator. They're taking, so we talked in your group, Yvonne, about this. It's the real and imaginary parts of the displacement operators. And then they have a D plus and a D minus. And then they're asking about the eigenstates of those. And they're showing the properties in the context of group theory. So it was kind of ignored. And then in 1986, so 12 years later, Jared Milburn, he was my postdoc supervisor. This is when he was a postdoc in Imperial College London. He moved to Canberra, Australia soon after, and then I joined him as a postdoc. But I know the stories about it. But when he was a postdoc, he was interested in not superpositions of coherent states, but he was interested in ways to represent the evolution, nonlinear oscillator evolution. So he calls it an anharmonic oscillator. It's not. It's more of what we think of as a Kerr nonlinearity oscillator. So the term anharmonic is a misfit there. People didn't keep that term later. So the term anharmonic disappeared, but the idea is correct. And then over here, so he said the Q function representation was good. So he picked a representation and then he simulated the evolution. He says, here's the coherent state. You have a position and momentum or position and momentum quadrature. This is the contour of the Gaussian. And then he lets it evolve. When it initially evolves, he shows that you get a banana state. This is the shearing effect. But over time, he shows that 1/4 of the period, it's a periodic revival, 1/4 of the period, he gets a superposition of 4 coherent states on a circle. And he shows that double that time, he gets a superposition of 2. But he doesn't talk about it in the paper. It just appears. So this is figure 8A and figure 8B. And I'm mentioning it because he doesn't discuss it. It's just a consequence where he's focused on the evolution. But this became a physical review letters paper based on figure 8A. And I'll show you this became a Nature paper. There's a whole Nature paper written about figure 8B. So it's kind of one of the richest papers I know in history where, you just pick some figures and they evolved into very important papers.
Sorry.
Yeah.
Why isn't a current nonlinear oscillator anharmonic?
Anharmonic in the books is you have x squared plus harmonic, x squared plus p squared, and then you add an x cubed for anharmonic. But this is an x squared plus p squared plus the square of x squared plus p squared. So it's more like we do with current nonlinearity stuff.
But it's not a anharmonic.
Yeah, it's exactly. Yeah. So etymologically, it's anharmonic, but it's not anharmonic. So he was not wrong in picking the term, but the term was hijacked by people to refer to x cubed. Good question. Okay. So then this is just a picture showing the evolution. There's the harmonic oscillator rotation. This is phase space, coherent state. And over here, and I'll go into it. This is a Wigner function representation. And then these are interference fringes showing that it's not just randomly choosing one coherent state or the other. Being able to detect this is important. But note, this is not observable. One does not measure. You can't just go sample the Wigner function. How to see that becomes a subtle issue that I'll go into. And then this became this physical review letter. So Yerke and Stoller, people who do superconductivity might know Yerke from that, but Yerke, before he did superconducting stuff, was doing other things. So then these guys at AT&T Bell Labs, they talked to Milburn, he's acknowledged, and they found that very intriguing, and then they investigated more. They made this slightly more general. So instead of the square of the 8 arrays, they allow cube and 4th power. So they did a few things. They added a little bit of decoherence in the system. What they did is mostly trivial, but what's nice is they go through the story of the cat state. So they don't know about this, but they're essentially writing a whole paper about figure 8A and what it means to have a superposition of coherent states. So they write about that. At the time, they, and I was around, like everybody just regarded science fiction. So it's a cute paper, kind of says, well, if coherent states are really classical and you could superpose 2 or more of them, then somehow you're borrowing the Schrödinger classical coherent state to describe typical wave-like optics, and then you superpose them. So it became, then the idea that these were cat states became important. Okay, this was the other one. So figure 8B became this paper. And this was by Wojtek Zurek, Nature 2001. So it's a whole paper on figure 8B. And this one is kind of a little bit harder to interpret, not totally relevant. But you can see it's a coherent state, a superposition of 4 coherent states. Now, when you take 2, you get these interference fringes. But in the middle of the 4, you get what looks like a speckle pattern. And this is what Zurek is writing about. So he constructs an argument here. And so first, it's a straw man argument. He says, well, there's an uncertainty principle and then the Planck scale. So Planck scale in his argument is not Planck scale that we do in, say, quantum gravity. Planck scale is the area of the contour of the coherent state. So there's a Gaussian state in phase space. And then there's a contour. That area is Planck scale. The interference fringes he calls sub-Planck. But if you only have 2 and you don't measure in the right quadrature, then you just see a mixture of 2 coherent states and no features. So you have to pick the right quadrature to see it. And he said, in this case, no matter which way you look at it, you will always see some interference effects. So you don't directly measure the Wigner function, but you'll always see some specular behavior that reveals quantumness. And then he says, phase-space structures associated with sub-Planck scales do not exist, or they do not matter. Here I show this common assumption as false. And I've done some sampling because I always wondered, was it common? I didn't believe this, but he says it's common, but I never found evidence for it being common. But he says this common assumption is false. they do not matter, non-local quantum superposition or Schrödinger cat states confined to a phase space, blah, blah, blah. He goes on, and then it's essentially Zurek cares about pointer basis. So a lot of Zurek's career is based on trying to show why the universe as a whole doesn't show quantum effects. And then he's trying to say there really are these effects, and then he wants to somehow find an intrinsic reason to rub out the effects. So it becomes like a straw man argument. He called them compass states because this state is the north, the south, the east, the west. So that's the compass state. Okay. So that's kind of early on where the field started. Now, making these, as I said, for many years, we thought that this would just be science fiction. I never thought it would ever happen, but anybody who knows me knows I'm a pessimist. So I think everything is going to be bad. But I didn't think it would happen. Then this interesting paper came out in Science in 2006, Philippe Grangier's group in Paris. So this came out, and this was interesting because they do some photon subtracted state. They get a Wigner function of this type, and then they kind of argue saying, okay, this is the first cat, but it's not a cat because the coherent state and its counterpart, opposite in phase, have significant overlap. So they call those kittens. It's kind of interesting too, just sociologically, because what happens is like, if you look at the Phys Rev Letters papers and things I have coming up, the titles are really boring and you have to read the paper. And so the American Physical Society has a language police that won't let you say things like QDID or CAD or anything. Even black hole, that was considered a dirty word, and then it was blocked for many years. But then you go to the Science, and then they'll let you talk about a kitten. I'll mention Yvonne's work where she could talk about anything. And so, if you go to Science or Nature, they let you put in fancy titles. So they had the kitten because there's the overlap. But did they really make one? Well, these things don't scale well. And so, I think, if you've ever heard the story, if it walks like a duck and quacks like a duck, it's a duck. And so they make something, and then they argue it's a kitten state because it's close in terms of fidelity to what the kitten is. So I thought this was really cute, nice work, deserved to be in Science, but it wasn't really a cat state to me. So that came out, and I wasn't totally thrilled. Then the group of Rob Sholkoff and Michel Devoret, Maziar on the theory and so on, had the work out in Science in 2013, deterministically encoding quantum information using 100 photon Schrödinger cat states. And then that was the paper where I thought, my goodness, of course I tried to find every reason why it was wrong, but it's good. It's a good paper. And you can see in here, in their figures, 3 coherent states, 4 the compass state. And what I find is cute here is they say using 100 photon Schrödinger cat state, but you read the abstract, it says 111. And so it's more than 100. So I always find it funny. Usually people try to brag, and this paper is the opposite. It's saying we got 100, but then the abstract says more. So they got so many that they don't even have to hype. And then, so it's 111 photons. They create a superposition up to 4 coherent states. That's the compass state. Something that always annoys me about that group, which is they don't know the history. So they put these things in and they don't know the compass. There's decades of history on studying these and they don't put that in. But it's okay. They did it. They don't need to know history, but I'm here to kind of correct the story. So you can see here that speckle pattern that Zurek had in the paper. So through the superconducting system, cat states became possible and irrefutably quantum. In the sense the coherent state, there's the Planck scale, the plus or minus 1 on the coherent state, and 100, take the square root, you get 10. So these Gaussians are so far apart that the overlap between the coherent state and its counterpart with opposite phase is really negligible. You'd really struggle to do an experiment to see that amount of overlap. So it blew me away. And then later, and this next paper came out, you can see Yvonne here. So Yvonne and Chen, I think you two were leading. Yeah. So the two of them leading the experiment, and they had a Schrödinger cat living in 2 boxes. And then you can see the 2 microwave cap. Yeah. So they did that experiment. They put some circuit diagram. So people like me who don't know superconducting that well would be able to follow in some circuit diagram what's going on. And then in this paper, it's, and I'll point out here, I don't know if I whined about it to you or something, but I did whine about it. Yeah. So they were doing it, and I'm kind of whining because I did stuff in the past, and it's this, zero history. It's a really good group, but in scientific history, it's Markovian. don't know what happened. And so you can see the effect of my whining over here, where it says, it's called the Schrödinger cat living in two boxes, but it's known as the entangled coherent states of theoretical studies 15, which is my paper review of entangled coherent states. So I whined about it, and then I got a mention. But you have to, there's a, the squeaky wheel gets the grease. So if you don't whine that you're ignored, you get ignored. That's the way it works. Okay, so that came out in 2016. And so to me, it's an entangled coherent state. And the reason I called those entangled coherent states, that was back in 1992, is because it gave like we cared about creating EPR states. We cared about creating entangled qubits or E-bits. And then, I kind of thought if we could make cat states, which was a big if, we'll also be able to make superpositions of pairs of coherent states. But what is the most interesting part is the entanglement part. So then I called those entangled coherent states to emphasize the entanglement. And then what makes it a little bit subtle is the coherent state and its counterpart are not orthogonal to each other. So a large part of what I did was to try to figure out with entangled coherent states how we deal with that overlap. Actually, the paper I wrote in 1992 had a very big error in it. It was Bill Monroe who corrected me, and then I had to write errata to fix it. This paper, by the way, very funny. So, like I said, it was like 1992. I named them, but I wrote a review paper where I point out that entangled coherent states actually go back to 1967. So here I am whining about not knowing the history, but I didn't know the history either. So I went through and I talked to lots of people. I started digging through the literature. Search engines became feasible back then. So I kind of searched everything. And then I realized that the theory goes back to 1967. It's a paper by Yakir Aharonov and Leonard Susskind. So they wrote a paper dealing with charge superselection. So I won't go into a lot of details, but essentially what they're saying, if you go to particle physicists, so particle physicists will show you a table of particles, quarks, gluons, photons, and blah, blah, blah. And then you say to them, well, could I have a particle in a superposition? Can I have a superposition of a neutrino and an electron and a gluino and whatever? The answer, of course, is yes, because of the nature of quantum mechanics, but they'll all say no. And why they say no, when they do it, like particle physicists think, look, can you have a superposition of two different charges? And particle physicists, and I've done this, and actually I'm going to CERN for 3 months, January to March, so I'll have a chance to probe lots of particle physicists, but they say no. And then what Aharonov and Susskind showed in 1967 is it's a belief in a super selection rule that really drives it. So the idea, they are actually adding an axiom to quantum mechanics where they say superpositions are allowed except the ones we don't like. That's what goes on. Quantum resource theory. So I was talking to Marco Tomomihil here about it, for example. And so the quantum resource theory people don't always know it, but it was born out of the super selection. I can trace the history. So the idea is that the reason that particle physicists will say it is we don't have the resources to prove to create these particles in superposition. They're not forbidden, but then you can start considering the resources to do it. So that's what it goes back to 1967. Funny enough, I told you that there was the paper by Dodonov et al. In 1974. That was the first cat state paper. But the first entangled coherent state paper was 1967. So oddly enough, you can see the first entangled coherent state in 1967. That's two modes. And then one mode is 1974. So history was kind of funny in that respect. Okay, so that's the idea. These things were built. And then here in CQT, you can see labs where similar things are built. So I leave the details for homework. You just go visit the lab. Okay, now that was the fun. This is about fun and profit. So now I'm going to go to profit. So the question is, can we use these things for, say, quantum information processing, quantum sensing, quantum communication? The answer is yes, yes, and maybe. I won't do the maybe. And so this goes back to, there's a nice paper by Ike Chuang, Debbie Leung, and Yoshihisa Yamamoto back when Debbie and Ike were students with Yamamoto back at Stanford University. And they introduced the term bosonic quantum codes. Now you'll see bosonic codes a lot. If you look at various companies like Nord-Conti cares about this, Xanadu to some extent, various other ones, like this whole idea that we're moving into this so-called continuous variable approach and encoding into it. The first paper that talked about a bosonic quantum code was this paper that came out of Stanford University in 1997. And I'll talk a bit about it. they do a bosonic quantum code for amplitude damping. So the idea is they're saying, well, quantum error correction is hard, but what if we just focus on errors to do with amplitude damping? And then they show that if you make cat states, if you encode into cat states, there's a way to be able to offset that error. So the idea was to try to reduce that error. So that's what they did. And then later, that was in the optical setting. And then later, there was a paper by Paul Coherent, Jared Milburn, who we talked about, Bill Monroe, who showed me my mistake in my entangled coherent states paper. They were at the University of Queensland in Milburn's group. In those days, we didn't care about order of authors. So the leader of the group's in the middle. Oh, it was alphabetical, I guess, probably in this case. Okay, so they were at the University of Queensland, and they introduced the macroscopically distinct superposition states as a bosonic code for amplitude damping. And the idea of this one is the paper is written for ion trap. And so I was with Dimitri's lab earlier today and seeing, so the idea, he's using these ion trap modes in the same kind of way. It doesn't matter if it's written for ion traps. The concept of playing with modes, you don't care which system you build. There's just a set of requirements for the math to hold. So everything they did holds in the optical case, in the superconducting case. It was just in those days, ion trap. At that time, Wineland's group was doing great work, and ion traps were kind of winning at the time. So that was the context. And then they put down Schrödinger cat states, kind of cautiously in parentheses because of the American Physical Society language police that still didn't allow a cat in a title. And then they say logical encodings. The paper cites the work by Ai Chuang, Debbie Leung, and Yoshi Yamamoto. And they went through encoding, how to encode a qubit. And then I was in Australia working there at Macquarie University in Sydney. And then I contacted them and said, hey, you can't do much with one qubit. You need qubit gates. And so then we introduced, I said, we need entangled coherent state qubits. And so we kind of completed the bosonic code story in this case by having one qubit and two qubit stuff. So we did that. It was minor impact, but it was kind of like getting the story right. Then a really interesting paper came out in 2001. It's very famous now. People talk about GKP this and GKP that. So it was Daniel Gottesman. After he left John Preskel's group at Caltech, he was at Microsoft, Alexei Kitaev, and then it was John Preskill. And so this is another language police story, because if you go to the archive and look up the paper, you'll see version 1 is called encoding a qubit in an oscillator, but versions 2 and 3 are qubit. And Physical Review said you can't put a qubit in the title. And so, but the evidence is there on the archive. And so the PhysRev A paper says that, but they even changed the archive paper. But essentially, it's interesting. So they cared about the same thing. It's like, how do you encode? You do bosonic codes. So in these things, think of this as a squeeze state. So it's a Gaussian, but squeezed so much the width is almost zero. And then two of these would be a cat state, but instead of Gaussians at what Zurich called the Planck scale, it's Gaussians at 0 scale. And you make a superposition of both, then that might encode a qubit. But they said, no, that's the way I think about it. It's like, okay, if you're going to make a superposition of two coherent states, why stop? Let's make a superposition of infinitely many coherent states of 0 width. So infinitely many squeeze state, why not? Well, and I talked to Dan Gottesman a lot about this. So like, to me, I would never have done it because I'm too mathematical. I think, well, the limit that the width goes to 0 and the envelope goes to infinity is not well defined. The limits don't commute. They did it, but they're smart. They knew they were doing something horrible mathematically. It's an infinitely many, infinitely thin coherent states, and that encodes the logical 0. Then and I call that a comb. That's in the abstract. So I call that a comb. And then you put another comb halfway between. That's the logical 1. So you have a spacing of 2 alpha, which is given by the amplitude of your coherent state, and you put 1 in there. But these are infinitely thin. So instead of putting this halfway between, why not put it a third, and the next one 2/3, and then you have a Q-trig. And there's no bound. So you can use this to encode QDITs. That's why the first version was called QDIT. Interestingly, if you do frequency stabilization conversion or an optical to microwave conversion, these are combs, frequency combs. So the same math applies in that case, and the same issues I have mathematically. Okay, so somehow that's the 0, that's the 1. And then if you do a Fourier transform, which optically you do by a delay line, the Fourier transform, you see how instead of 2 alpha, it's 2 pi on alpha. So a Fourier transform takes the width of the teeth of the comb and the width of the comb and swaps them. But because these are infinitely thin and infinitely long, you swap two infinities, you just get the same two infinities. But if you put a width on it and you put an envelope on it, your envelope and your width change. And so this is the Hadamard transformation, going from 0 and 1 to a superposition of 0 and 1, and that's just done by a delay optic. So this was a very intriguing paper because it kind of gave away, very bad math, and we don't know how to make the state, but it kind of opened the door for thinking about how we could go from a continuous variable setting into being able to do quantum information processing. So whereas the stuff I did was really about 2 of them with width, that goes for. Then they go through in the paper and they don't say, I don't know why it's double, but they don't say clearly, but what they do say is, we can't do that. They don't say why, but it's fundamentally impossible. And so they do put width on the teeth and they do an envelope around the set of teeth. And then your logical 0 and your logical 1 are no longer perfectly orthogonal, because if you have a 0 and then the 1 is you slide the teeth halfway between, and you do Fourier transforms where you swap them, things don't go right. And so I remember back when Perimeter Institute was founded, 2001 or so. So soon after the paper came out, Dan Gottesman was there. And I went up and I asked him, because he's a quantum error correction expert. And I said, well, I didn't get it. I thought, okay, I'm going to try to work on quantum error correction. And at the same time, many other people looked at this and thought, how do we do quantum error correction? And I asked him, I said, how do you do the error correction on this? And he said, that was Kitaev. So it was Kitaev wrote that part. So somehow he absolved himself. And then I tried to ask Kitaev, but I couldn't get an answer. So they wrote it. They kind of had the idea, but it wasn't there. Even today, we struggle with it. So there are companies that are working on this kind of encoding, but how exactly we do the quantum error correction is a big problem. And it's a problem for the companies going this direction. And it's gradually getting solved, but the rules of quantum error correction are being bent along the way. So nowadays, old days, you have a talk about quantum error corrections like Shor and Steen and that. And nowadays, you don't even know what the next person to you means when they say quantum error correction. Okay, and then they go through circuits to do it. And they also explain how they can do all Gaussian preserving operations, provided they make cubic phase states. And I know here, again, the Dimitri's group, they're trying to make cubic phase states. And so these things are going on. And here at CQT, you can go visit a lab and see the effort to make it. Okay, so me, more mathematical in my heart, I thought, okay, well, fine. Those are coherent states. I branched out in a different direction. I thought, okay, coherent states don't have to be with an oscillator. And what happened was in 1970, there's a paper by Arecki, Gilmore, Clowder, I forgot the other ones, but they introduced what were called atomic coherent states in 1970. And so atomic coherent states are interesting. If you think about atomic physics and you label the levels, you got N, L, M, S, right? This is what you learn in textbook. But if your electron is high up in what's called Rydberg atoms, it's not a very good representation, because for highly excited atoms, your electrons behave like planets. They orbit the nucleus. So the idea is that once you identify the groups of these things, instead of NLM, which is the particle-like description of atoms, what would you do for the wave-like description? And the answer is you need to adapt Glauber's coherent state idea. So they did that paper in 1970. And then in 1972, Korolemov wrote this paper on coherent states for arbitrary Lie groups. He says, the harmonic oscillator, I think he writes it here, is the nilpotent group of Weyl. So that's just the harmonic oscillator algebra. And he says, okay, fine. What if you have a different group besides the nilpotent group of Weyl? What are you doing? He said, you give me any Lie group, which means, given a Hamiltonian with any known symmetry, he can tell you what the coherent state is. So he goes through and in the spin system where you've got, some 2J plus 1 levels, he just says that instead of using the phase space as a plane, make the phase space a sphere. And then there's a blob. Instead of a Gaussian, it's a binomial distribution. In the limit that your sphere gets large and this gets small, binomials converge to Gaussians. So that's practically what happens. But he gives a recipe to be able to construct coherent states given any particular Lie group. So I started thinking, okay, maybe I'll work on cat states for that. And here, this paper, I wrote a paper back in 1989 where I was a postdoc with Jared Milburn. So he taught me, I understood what he did. And then I just took a nonlinear evolution. So I said, start with that binomial distribution. We didn't have good plotting back then. So like nowadays, you just do a plot. In those days, everything there, I had to write my own plotting package. When I first started, I even had to write the script for where the pen would go. But this one, I had to figure out how to plot it. And so in this case, I didn't know how to plot the sphere. So it's a plot on the plane. It's a stereographic projection. It's one of two conformal maps of the sphere to the plane, and it also preserves circles. So when I make my, this is the coherent state, the circles map to circles by that mapping. They're not concentric, but I thought a long time about how to represent. Nowadays, we would just plot it on a sphere. And so the idea here is I took the same nonlinear oscillator, or as Tim says, an harmonic oscillator, if we split it up. I let it evolve, and of course it shears. So that's banana state on the sphere. And then the banana turns into a superposition of two coherent states or a compass state or anything. So the purpose of doing this paper was taking the same nonlinear evolution and showing that the way of producing cat states map over. So I took the Paralymov coherent states, the nonlinear evolution that Milburn studied, put them together, and then I can consider cat states for any symmetries, any group symmetries for Hamiltonians. And so that was it. And then I went a little bit crazy and worked on SU11 and other stuff. It's not that crazy. Actually, one day I think there'll be experiments, but I went further. This turned out to be useful. So this is part of the quantum sensing story. So this paper, 1996, from Dave Wineland's group. So and they wrote this paper, and I was a referee of that paper back then. Alexei Gorshkov, if you know him, he gave me a hard time over this because said that paper should have been in PhysRev letters and was it my fault? But no, the paper was really submitted to PhysRev A. And so they essentially said the following. Okay, so if you now think about accuracy, if you want to get the frequency precision of your clock as good as possible, then you might consider every ion in your trap is an equal superposition of ground and excited. So you have a tensor product of each atom in a superposition of ground and excited, and then you can estimate, you can get an error on your frequency estimate that scales with the square of the number of ions. So in a clock setting, it just says, if you want to double the precision of your clock, quadruple the number of ions. But they said in this paper, well, what if we did the following? We say, it's a GHZ story argument. We make all ions in a superposition. The ions are all ground superposed with all excited. And then they show that instead of quadratic cost, so quadruple the number of ions to double the precision, you double the number of ions to double the number of precision. And this is related to noon state arguments and all that. But when I was refereeing it, I could see there's another way to think about this. So there's a mathematical argument in Schur-Weil duality. I won't go into the math, but essentially, if you say that, it's really a system where you say the physics for every ion is identical, you then get a permutational symmetry on the system. And this is effectively a superposition of all ions in the ground state and all ions in the excited state. So what they proposed here as a way of enhancing clock performance is exactly what I have here. So, but I didn't see that application. But the math of what they did is the same. The symmetries are the same. And so it's saying that superposition of spin coherent states is valuable in one application by enhancing the clock standard. But in the whole field of quantum sensing, if you dig deep and look at what it's about, I have to be careful because different ways to define quantum sensing. But in a very purest sense, the idea of quantum sensing is a scaling argument, just like quantum computing is a scaling argument. So you say, if I want to sense something, how much sampling do I need to do to estimate a value? And then quantum sensing related to the Cramér-Rao lower bound, which is related to Fisher information, is you want to reduce your sampling so that you don't get this square root. So essentially, instead of paying a quadratic price to estimate, you get a subquadratic amount of sampling. That's the whole idea. And that's captured in their argument. And then this argument comes up, and then it ties with the whole noon state argument. Okay, now, so I want to leave, so 5 o'clock's the end. I'm going to leave time for questions. So I like questions. So I'm going to try to wrap up in the next 5 minutes and then leave plenty of time to discuss. So this one, I'm going to go through what I'm doing with Andrea Morello and his group. And these pictures are from our Nature Physics paper from January. And so these are pictures from the paper. I'm going to explain what they mean. So here we identify a single antimony Sb nucleus, isotope 123, and the spin is 7/2. Okay? So there's one nucleus that we identify. It's sitting here. We have different ways to control, which is microwave lines, electric field lines, and magnetic field. So magnetic, electric, and whatever. And there's the nucleus that we identify. And so we're essentially picking one nucleus and playing with it. I'll talk about it. I often have discussions with the cold atom people where they'll have a gas of cold atoms and then we compare results. And we have some very rich things we could do here outside the reach of the cold atom people. But when I talk to cold atom people, it's always saying, no, we are really just studying one nucleus. And that nucleus sits in a silicon substrate, and we need to have it silicon 28 because we don't want spin to interfere. And then the antimony nucleus has 5 outer electrons. So 4 of them are attached to silicon nuclei. There's bonding to silicon. And then by applying an electric field, we distort the medium and the nucleus. So to me, the nucleus is just a ball. And when we remove one of the electrons, we ionize it, that ball lives decoupled from the whole universe, except the microwave field affects it. So we essentially decouple it from the universe, but we apply electric field to apply a torsion to the nucleus. So the nucleus, instead of being a spherical ball, starts to get a little bit of a twist to it. So it's undergoing torsion effect, and the torsion effect gives it a nonlinearity. And I told you earlier, to make the cat state, you need the nonlinearity. So we distort it to make it effectively a nonlinear oscillator, but it's spin, not harmonic oscillator stuff. And before we begin, there's the extra electron attached. And then what we do is we prepare the nucleus in the state that we want by doing what's in the field of electron spin resonance. And so by playing with the hyperfine coupling between the electron and the nucleus, we're able to prepare the nuclear state. Then we ionize it. We rip that electron off. Then it's just this ball with torsion hanging alone in the universe. Then we apply microwave fields to be able to make things happen. And then we reattach the electron and use electron spin resonance techniques to read the state. So that's what goes on. And so our electron spin resonance is reading different levels, and then we start to infer what's going on. These are representations that are Wigner function-like, but they're for spin systems. So a little more subtle how they work, but they're good representations. And then these are representing the states we make. This is the cat state that we make. So it spins 7/2. There's 8 levels. The north pole is the spin up, very up. The south pole is spin down. And these fringes are the fringes that you see in the cat state for the oscillator. The way to think about it on a very physical level is you have this ball alone in the universe, and this state is the ball is spinning very fast this way. And this state is the ball is spinning very fast that way, but we create a superposition. So our nucleus is in a superposition of a fast spin with the opposite, and then the fringes show us that the fast spin in each direction is interfering. So that's what's going on there. Now, what we do, there's a lot of quantum control that goes into it, and I won't go into the details, but what did happen when I started working with the group, and I was talking to Valerio so Valerio's group is also collaborating with them, and so they've been doing work, and I was talking to Valerio yesterday about this, and it's, so what we brought in, I think since yours, did you check if yours had a multi-tone control? Okay, no, yeah. Okay, so Valeria and I talked about it, but I think the work didn't happen. So when I was talking to Andrea, and something I'm talking about here too, is there's a decoherence effect. How do you make this cat in a way that you can do this and do the operations you want fast enough that the decoherence doesn't kill you? Thank goodness the decoherence is very low for a ball isolated in the universe, but it's still there because of control fields coming in. And so essentially what we want to be able to do is change the state of this nucleus. Now, in a linear system, so if there's no torsion on the nucleus, then the energy levels for the spin are equally spaced. But in a spectral way of thinking, the effect of the nonlinearity is to make this ladder uneven. The same with our oscillator. You make a nonlinear oscillator, it makes it uneven. So we have 7 different frequencies to go up 8 levels in our spin 7/2 system. And originally the idea is, okay, you start in some state and then you make a superposition and then you ladder it up. You just do a set of Rabi flops, take it up to the top. But in a quantum, it's kind of like I have some very mathematical way of thinking, but at the pedestrian level, it's more if you're going to do it. So it's kind of like, how do you climb a ladder in a quantum world? So if I make a ladder to go up and change a light bulb, in a quantum world, I'll make the ladder so the steps are unevenly spaced, which means as I'm going up the ladder, the energy of the step depends on which step I'm going up. So that's the first thing. And then when I go up the ladder classically, I do first step, second step, third step. In a quantum world, I don't. I apply superposition of all energies for each step, and then I just go up the ladder much quicker. So we're essentially with our multi-tone control, we climb the ladder in superposition, and we're able to do our operations better. On a quantum control side, it's really just about how do we devise these control schemes? And there's a lot of subtleties. Like I said, if you're going to climb a ladder in a quantum world and you apply a superposition of all energies, but the energies have different frequencies, and then how much amplitude you apply is also very subtle. So there's a lot of subtlety in the quantum control limit. You put too much power in, you burn things out. Okay, so we essentially go up, and then by doing very good quantum control techniques that are partly driven by intuition, and so like I said, many years ago, I would think, what's the coherent state for the system? How do you then do the transformations? By drawing on that intuition, there are then very nice ways to make cats and control cats driven by that. And so, we're entering a very interesting world of cat control. Your computer hijacked. I think that's good. I can stop.